select best of you actually did the video worksheet, which is awesome. So thank you for doing that. Do understand, ladies and gentlemen, in order for us to not crash Infinite Campus, we have to assign all the assignments that are due this week to be due on the 11th in Canvas. So you'll notice on the module it says due 10/4 on the title. We have to make all those assignments that are assigned this week and due this week, we have to make them due logistically on the 11th. Otherwise, it throws Infinite Campus out of whack. So does that make sense? So it's not going to be in your to be graded section of Canvas. You just need to know that you have assignments that are due this week that will be technically due on Monday. So if I get anybody coming back to me on Monday saying, Mr. Byers, how come you assigned 6 things for Monday? That's a lot of work to do over the weekend. I'm going to be like, you're an idiot. So because of this. So just realize that. So hopefully you guys realize that there was a video worksheet. I didn't mention that on Friday. That was due yesterday, but you could do it tonight too. Yeah, so there you go. All right, so we're starting a new unit. 2 units ago, we talked about what was going on in the nucleus of an atom. And this unit, we're going to be talking about what's going on with the electrons. So we got our protons and our neutrons. And hey, look, it's a helium atom. So with this unit, we're talking about what's going on with the electrons. And specifically, how electrons can move between energy levels, which makes sense if you were to video what those are, energy levels around the nucleus. Now, obviously, this is grossly out of scale, but you'll notice when an electron is in a low level and it gains energy, it jumps up. When an electron is in a higher energy and it loses energy, it jumps back down. So we pretend that our electrons are in shells. So there's a shell, we'll call that shell number 1, and there's a shell, we'll call that shell number 2, and there's a shell, and we'll call that shell number 3, and that's about as far as we're going to go because we don't want to go into too great detail. But I need a volunteer. Anyone want to volunteer? You do get to stay behind the camera, so you don't have to be like, you just have to stand up. That's all you have to do. Stand up. Okay, now I have to remind myself how to get your name wrong. Talon?
Yes.
Okay, so Talon. So Talon is at level 1. She's on the floor. There is no more lower that she can go in the room. The floor is as low as she can go. Make sense? Okay, so Talon, I'd like you to stand on your chair, if you wouldn't mind, please. So now she is at level 2. To get to level 2, her muscles had to exert energy to lift herself up to level 2. Make sense? Okay. Now she can also find a level 3. So find a level 3, and she once again, the energy that her muscles exerted pushed her body up to level 3. Now she has some options. In coming back down, she could jump all the way down to level 1, or she could go from level 2 to level 1. Make sense? Now what I'd like to do is find somewhere to stand that's right between level 2 and level 3. So right between level 2 and level, so somewhere between level 2 and level 3. Okay, so now you're on level 2 again. So somewhere between level 2 and level 3. Okay. The point is, it doesn't exist. Thank you. Yay, Talon. So the point is, it doesn't exist. There is no place that she could stand that exists between level 3 and level 2. Similarly, there is no place where she could stand between level 1 and level 2, because the places she could stand are what are called discrete. So this is a word you should probably learn. Discrete means this much and no more. So, like if you go into Walmart to buy the new Call of Duty game, and you go in with $20, are you going to be able to walk out of there with the Call of Duty game?
Is it on sale?
No, it's brand new. It's $70. Because anyway, but the point is, things have a very specific cost, and if you try to buy something with less of that cost, you don't get that thing. And if you go in there with more than that, you buy the thing and you get some back. And that's how energy of electrons work. The electron can exist in level 1, it can exist in level 2, and it can exist in level 3. But there is no place for it to go in between the levels because the levels are discrete. An electron can exist in discrete levels. It can't be anywhere between. So far, so good? Does that concept make sense? All right, so now let's attach some numbers to it. Let's say, let's make things really simple. Let's say level 1 is 0 units of energy, and level 2 is 4 units of energy, and level 3 is 11 units of energy. If I hit this electron with 1 unit of energy, what happens? Exactly, it stays put. Nothing happens because it doesn't have enough energy to get to the next level. If I give it 2, what happens? It stays put. Nothing happens. Give it 3, what happens? It stays put. Give it 4, what happens? Yeah, if I give it 4, this electron is going to jump up because I gave it 4 units of energy. And it went from 0 to 4, it needed 4, it got 4, it jumps up. Make sense? Now, if I gave it 5 units of energy, guess what happens? If it's here and I give it 5, what happens?
It goes up to level 2.
It just goes up to level 2.
Yeah.
And that extra unit of energy just passes right through the atom. If I give it 5, 4, jump, 1 more passes through. If I give it 6, same thing. But if I give this atom 7, there's a difference between 4 and 11. If I give this atom 7, then this electron or this electron will jump up here because the difference of 4 and 11 is 7 units of energy. Make sense?
Oh, yes.
So these levels are discrete. And by the way, there's 7 different levels, all of different sizes, depending what the atom is. But yeah, so if I give it 1 or 2 or 3, nothing happens. If I give it 4, it'll jump up. If I give it 5, it'll jump up. If I give it 6, it'll jump up. If I give it 7, then the electron in level 2 will jump to level 3. And the process continues. Okay? And these jumps have special names, which we're going to get to. Now, give me a thumbs up if that makes sense to you. All right, cool. You guys get the benefit of, I know where the pitfalls are, so I know what to explain more often after second period. They're like, I don't get it. It's like, sorry, okay. I'll remember so I do better in 5th period. Okay, so there's this guy named Ernest Rutherford, and he was a British physicist and chemist. Actually, there wasn't really chemists back in Rutherford's day. It was like 140 years ago. There wasn't really chemists. There were just physicists, scientists. And he did some investigations on energy and nuclear particles. And one of the things is he and this other guy named J.J. Thomson came up with this idea of electrons. And what was typical back then, because literally the number of scientists working in chemistry and physics was like double digits, like less than 100 worldwide. His student, Niels Bohr, a Danish physicist, took over his ideas and said, you know what? The electrons are in discrete levels. So there's multiple levels, again, just like we did level 1, 2, and 3. Electrons can exist in these levels, but they can't exist in between the levels. That was weird. Okay. I don't know what that was. There's Niels Bohr. And he founded the idea of quantum science. Of course, this is from Latin. Quantum is a packet of a specific size. Okay? The amount of energy between level 1 and level 2 is a quantum of energy. There is a quantum of energy that must exist between specific size, between these levels. Quantum is the singular of quanta. So when you blast it with a whole bunch of energy, you're blasting with quanta. The single jump is a quantum. Kind of like if someone takes your phone and they're looking through your phone, they're getting your personal data. Probably never heard of this word. A singular point of information is a datum. You ever heard about that?
No.
Now you have. So data is a multiple of datum. A singular piece of data is a datum, and all of it is data. Similarly, a singular packet of energy is a quantum, and multiple is quanta. Just kind of wild. So That's the idea. The quanta is of a specific size. It is a discrete amount, no more, no less. Kind of like when you go buy something, you have a specific price. It is no more, no less. You give it more, you get the extra back. You don't give it enough, you don't get the thing. Okay, so, all right, so electrons are in the ground state. This is the lingo we're going to use. Ground state, that is where the electron exists to begin with. Okay, that electron is in its ground state, that electron is in its ground state, that electron is in its ground state. It absorbs energy. And the energy gets absorbed, and what does it do? It jumps to what's called its excited state. Okay. And that's the lingo we're going to use, ground state and excited state. Takes in some energy, jumps to the excited state. Now for 19 years, for 20 years, I've taught it this way, that then a moment later, what does that electron do? It jumps up into its excited state. A moment later, what does it do? Take a wild guess. It goes back down, exactly. And it goes back down. Now I say a moment later, but thanks to Marvel and Endgame, we know that things that exist at the quantum realm, time doesn't really exist. So according to us on the outside realm, it doesn't happen a moment later, it happens instantaneously. The moment the electron jumps up to the ground state, it also jumps back down to jumps up to the excited state, it also jumps back down to the ground state. Thanks, Marvel, because we know that energy doesn't, or that things in the quantum realm, time doesn't matter. Time doesn't work at the quantum realm. Okay, does that make sense so far? Now here's where things get really interesting. I'm going to give it some electrical energy. Some atoms, when you give them electrical energy, they emit, not electrical energy, they emit light. And that's what's going on in here. Electrical energy from two AAA batteries are going into the molecules, and the molecules are emitting visible light. So let's say this electron jumps up 4 and jumps back down 4. When it jumps back down, it might give off a red photon. A photon is a single piece of light. It is a quantum of light. Does that idea make sense? It's like, bloop, single photon. Your eyes cannot see photon. Your eyes cannot see a photon. Your eyes need to see billions of photons in order for them to register. But a photon is a single quantum of light. So it's going to send out a red photon. Now maybe this electron jumps up here and jumps back down, and oh wait, we're going to call this -4 because it lost energy. And this one jumps up here, 7 comes back down 7, and that transition down here, -7, maybe that one sends a green photon. Maybe this one down here gets the entire 11 units of energy, jumps up here, but then it drops all the way back down at -11 and comes back down. It might send out a blue photon of energy. The amount of energy that comes out is identical to the amount of energy that goes in. But what comes out when it comes out as photons tend to be different colors. Blue light has more energy than green light, which has more energy than red light. Okay. And the highest energy, maybe it comes out, maybe it jumps like a whole bunch forward and a whole bunch back, it might send out ultraviolet. Or maybe it's just a tiny transition, it might send out infrared. But the idea is the transitions between energy levels will send out visible light of different wavelengths depending on energy, from low energy red to high energy blue, and so on. And that's all a piece of atomic absorption. So here's a great example. These are different wavelengths of light, animated, obviously. You see the red is moving with big bumps. It's got it kind of lumbering along. And this poor little blue guy is just bump, bump, bump. Go away from me, guy, away from me. The blue photon is actually a more energetic photon. And we'll talk about why that is in a little bit. Okay, so these are like A small gap will send out a red photon. A bigger gap might send out a yellow photon. A medium-sized gap might send out a green or a blue photon, and a big gap will send out a violet photon. And a huge gap will send out an ultraviolet photon. When an electron gains energy, we call it atomic absorption. It has absorbed the energy, jumping into an excited state. And again, requires a specific quantum of energy. And that quantum of energy is different for every atom. It's different. Every atom is a different arrangement of their shells and how far away they are from each other. Atomic emission is what you get when the electron returns back to its ground state, releasing the energy that it had absorbed. Some things, like metals, will absorb electricity and emit electricity. Some things, like whatever they use to make this laser diode, will absorb electrical energy and emit light energy. Lasers. Okay. Questions so far? Yeah.
What's electrical energy?
What is electrical energy?
Yeah.
A steady stream of electrons traveling from a high potential to a low potential. Kind of like water in a hose.
So it's like, I don't know,
Yeah. So you basically
like a domino effect.
exactly. Yeah. Precisely. I usually, when we talk about electrical energy in physics, I usually talk about, imagine a tube full of water. If you put water in one end, it has to come out the other end, but it's not the same water. So you hold the hose like this, somebody turns the water on, it hits you right away, even though the water has to travel through the holes, or through the hose. So that's basically, or you can also think of it as a tube full of marbles. Imagine a glass tube full of marbles. You put one marble in one end, it pushes one at the other end. So you put matter full of electrons into an electric field, and it causes the electrons to move, and one goes in one end and pushes the other one out. That's electrical energy. So take physics. We'll talk about that in the spring. All right. Any other energy or any other questions before we move on? All right. So again, here's a couple pretty cool diagrams. This is like the best. I found this online about 6 years ago and I stole it. I haven't looked back because it's awesome. Okay. So in 2018, somebody asked, what causes the northern lights? You know what the northern lights is? The aurora borealis? You see pictures of it. Anyone actually seen it live? You don't see it in Vegas. You have to go way up north, like Canada. But basically, the sun is constantly ejecting tons and tons of particles and bathing the solar system in these particles. The Earth is unique, particularly, because it has a spinning molten metal core that creates a magnetosphere. I'm not joking, it's called a magnetosphere. It's basically a shield that goes around the Earth. So the solar wind is constantly blasting everything in the solar system, and we happen to be in the solar system. And then the magnetosphere directs most of those harmful particles, they just bounce off of our magnetosphere. But when something bounces, it loses energy. I can prove it by throwing a ball at you. If I bounce this ball off your head, it's going to lose a little bit of energy and impart that energy to your head. Believe me? You will not believe me? Or arm. So it imparted some energy to your arm, and so it slowed down a little bit when it hit you. Same thing happens here. The particles hit the magnetosphere, they slow down a little bit and lose energy, and the energy that they lose causes the molecules in our atmosphere to give off light. So kind of a slick deal. That was wrong. There we go. So, hey, there we go. Come on, move this way. So the charged particles strike our atmosphere, bounce off the atmosphere, lose energy, and they cause the gases in our atmosphere to get excited and give off visible light. And that's why you get these crazy bands of light in the atmosphere. Yeah, pretty neat. You'll have to travel 1,000 miles to see them, but still pretty cool. All right, so this is the electromagnetic spectrum. When I say electromagnetic, what I mean is these are all of the waves that can be created when electrons jump up, and we'll do math soon, I promise, just hang in there. This is so boring, I hate Mr. Fire. Because there's formulas. So electromagnetic spectrum, these are all the waves, all of the photons that can exist in our universe that we know of from things we can see, this tiny slice of light. See, this says the UV visible spectrum, and all that light kind of funnels down to one point. This tiny, tiny slice of light, that is what our eyes can detect. Some insects can actually detect into the ultraviolet, and birds too. They have chemicals in their eyes that can actually detect all this down here, but we can't. But we can detect everything here. But all of this is technically light. It's all light. One second. The radio waves, do you know what this is? You know what this is? It's a phone. But at the heart of the phone is a radio. This is a radio. And it's constantly in connection with towers somewhere else. Using pretty much the exact same science that existed back in the 1920s, we send radio waves to a tower and they send them back to the phone. The difference is they took the technology and basically turned those radio waves into little bits of yeses and nos, which create data. But this is basically a radio. It's constantly sending radio waves out to the tower, and the tower is picking them up and sending them back. And how often they send them turns into data. But it's a radio. So you have little radio waves that are coming out of your pocket or your butt, depending where you get them. Okay.
Would it theoretically be possible to make a wave with the wavelength of Planck?
Theoretically possible?
Yeah.
Yes. But that would be such a massively high energy that would be such a massively high energy transition. I don't think that matter has been discovered yet. But yes, technically, sure, possible. But nothing on our periodic table could do that yet. Okay, so anyway, so that's the continuous spectrum. The part of light we can see is the continuous spectrum. The whole thing is technically light. From X-rays we use to see your teeth and they get stuck in metals, to radio waves that we use to make phone calls or watch TV over the air. Okay. It's all light. And here's the crazy thing. All light has a speed of 3.0 times 10 to the 8th meters per second. C equals lambda F. So our formula, let's get rid of our nucleus here, our formula for all electromagnetic radiation follows the same pattern. C equals lambda F. And C is the speed of light. And the speed of light is 3.0 times 10 to the 8th meters per second. What's lambda and F? Lambda, this is going to come up on the next couple slides too. Lambda is wavelength. And it's measured in meters. And F is frequency, and it's measured in 1/seconds, or hertz. The takeaway from this page is this. All light travels at the same speed. So whether it is a super low energy radio wave that's constantly traveling through your junk because you put your phone next to your pants, it travels exactly the same speed as a high energy gamma ray that if you put that next to your junk, you'd probably be sterile after a couple days. All travels the same speed. Do they all have the same amount of energy? No. The waves that have a high frequency, E energy is Planck's constant times frequency. You asked about a Planck, so that's a Planck right there. So energy is Planck's constant times frequency. High frequency means high energy. So everything over here is very high energy. Everything over here is very low energy. Okay, let's move on. So there's what I was talking about. So you have super high energy little blue guy because he has a high frequency, high energy. And if your frequency is high, your wavelength is small. If your wavelength is big, your frequency is small because the product of the two are a constant at the speed of light. So the typical exercise that you will have a very good chance of getting on a test in a couple weeks is high energy X-rays and low energy radio waves travel So does a high energy radio wave travel faster, slower, or the same speed? You know that a high energy X-ray travels what? Compared to a low energy radio wave, a high energy X-ray travels same speed. Even though one has a lot more energy, like billions of times more energy per photon, they travel the same speed. Okay, so C equals lambda F. Therefore, wavelength and frequency vary inversely. They are inversely related, meaning high wavelength, low frequency. High frequency, low wavelength. That's what that means, varies with. And energy varies with frequency. The energy of a photon is equal to Planck's constant times frequency. What is Planck's constant? It's a number that turned out to work pretty well. It is a fundamental constant of the universe, kind of like speed of light, and we name it for this guy named Maxwell Planck, who, much like you, was bored in his science classes, and eventually he figured some stuff out. Evan, question?
So is amplitude just caused by multiple photons of the same wavelength, kind of helping each other out?
Yes.
All right, that's what.
Yep. Okay. Are we good so far? Give me a thumbs up if you understand this stuff, or at least are ready to move on and sick of me talking at you. Yeah, let's do some exercises then. How fast, this is the part where you actually are becoming an active participant in your learning. How fast is an X-ray of wavelength 3.2 nanometers traveling?
C.
Exactly. It's all traveling C. How fast is a low energy radio wave? It's moving at C. How fast is a photon of gamma rays? C. Cosmic rays? C. Cosmic rays are so energetic they don't even enter our atmosphere because they just blast away anything they hit. They don't even make it into our atmosphere. But low energy radio waves, moving at C. Light waves, moving at C. A little green photon, moving at C. Now, that doesn't require any math because they're all traveling the same speed. This one does require some math. What is the wavelength of a radio wave with a frequency, that's F, of 2.3 times 10 to the 9th hertz? This is going to require some math, and there's your formula. So take out a calculator or something to write on, either paper, your neighbor, board, table. This tooth.
It's just like normal.
I don't see it. Yeah. And we'll make reasons, but that's fine.
What do you guys usually?
2 hours. Where you guys?
We ended.
Let's go at it.
Well, it's supposed to be that. You guys know that. No, most of them.
So for those who are having trouble getting revved up, you're looking for lambda here. So you're going to put your calculator 3.0 times 10 to the 8th divided by 2.3 times 10 to the 9th. And it's going to give you a number about the size of your cell phone. That's not a coincidence. That's a 2, by the way. Peacock 0.3. 2.3. Okay. If you got an answer, give me a thumbs up. Okay, take 1 more minute. Okay, If you get a number less than 1, if you get a number less than 1, raise your hand. Looking good. Less than 0.5? Good. Less than 0.1? Good, yeah. So what'd you get? 0.13 meters. That's about that big. It's not a coincidence that your cell phone is limited in how small they can make it, because your cell phone has to send out radio waves, and there's a limit to how small they can make the antenna to communicate with the towers. That is the typical wavelength your cell phones put out, or typical, wavelength your cell phones put out. So they have to basically make an antenna about that size, or a multiple of this size. Otherwise, it doesn't work. So you're like, that whole thing, like, I'm gonna have a cell phone that like fits in my ear. It's like, not unless the technology changes. You might have a radio, but your cell phone is of a certain size, because that's the size the radio wave has to work to send out stuff. Okay, what is the frequency of a 500 nanometer? Oh, look at that. 500 nanometer laser light. So this is my 500 nanometer laser light. Nano means 10 to the negative 9. So nano means 10 to the negative 9. So you're familiar with milli? The thousandth is milli. A millionth is micro, and a billionth is nano. There's the metric conversion right up there. So to put in 500 nanometers, you need to put in 500 exponent negative 9, or 500 times 10 to the minus 9. I don't know why there's weird noises come up from my computer. There we go. Did I get an announcement of some kind? That's turned off. Let's do this one. So now we're looking for the frequency of the laser light.
Did you do it with those originally, or did you do
These
it?
exact numbers.
That is, you have to have it with the, yeah.
You just told me not to.
No, you have to use a certain configuration.
So it's a separate.
So for those who might be getting still warmed up, you are now solving. This is wavelength. If it gives you something in meters, that means it's wavelength. So we're actually looking for frequency, and frequency is going to be the speed of light, 3.0 times 10 to the 8th meters per second, divided by the wavelength, which is 500 times 10 to the minus 9. And yeah, it's going to be a big number. What do you got?
6 times 10 to the 14th.
Yeah, 6 times 10 to the 14th. So 6.0 times 10 to the 14th. And the unit is 1/seconds or hertz. By the way, why is it 1/seconds? This is why. In all of chemistry and physics, the units need to cancel out. So in our wave formula here, C is meters per second. Wavelength is measured in meters, so the units have to cancel out on both sides. The units have to be the same on both sides, which means frequency has to have the unit of 1/seconds or per second. So if you've ever heard about, like, I have a 300 gigahertz computer. This is a 2.2 gigahertz computer. Hertz means how many times it does something every second. Like most computers, like your cell phone probably runs on a 1.4 gigahertz processor, which means it makes 1.4 billion calculations every second. That's what gigahertz means. 1.4 billion calculations every second. Okay, are we good? Did we get this? Okay, last thing for this idea, how much energy does each photon of the above green light hold? So the formula is this: energy equals Planck's constant times frequency. And Planck's constant is 6.63 times 10 to the negative 34 joule seconds. So this is your frequency that you're going to plug in here, and Planck's constant, 6.63 times 10 to the negative 34. It's going to give you a tiny, tiny, tiny amount. But that is okay. We care about things even when they're small.
Yes, it's negative 345.5. Pretty sure. Yep.
Okay. So again, Planck's constant is one of those things. It's one of those natural numbers that just comes up in science, and it is 6.63 times 10 to the negative 34 joule seconds multiplied by the frequency of our wave, which we just figured out to be 6.00 times 10 to the 14th 1/seconds. So if you take a joule second and you multiply it by a 1/second, what unit are you left with? If you have a joule second multiplied by a per second, what unit are you left with?
Joule.
A joule. So this is one of those crazy test-taking strategies that I'm going to mention to you now because the PSAT's coming up. And this might come up very handy later on. If you cannot cancel the units, your answer is wrong. If you can cancel the units, your answer might be right. So just like in math, if you multiply length times width times height, and it's meters and meters and meters, your answer should be in cubic meters, right? If you do a math exercise and your units cancel out, you know you're on the right track. If your units don't cancel out, you know you're on the wrong track. If you have a multiple choice question and the units don't cancel out, you know that option is no good. Make sense? You don't even have to do any algebra. You just have to look at the units and like, oh, those units don't cancel out. I got meters times volume, and they're coming up with, I don't know, kilograms or something. They're like, no, those units don't cancel out, so it doesn't work. So joule second over per second is joules. So when you do all this, what is the energy carried by a single photon being launched out of my green laser? Anyone know what it is? What do you got, Evan?
3.978 times 10 to the negative 19.
Yeah, 10 to the 19 joules. So that's not very much energy. So there's a single photon is not very much energy. Even if it's a really high energy photon, it's not a lot. But when you get a lot of them together, you can do some damage. Anyone want to prove it? I can shine this in your eye. It's not going to feel good. No, I wouldn't do that to you. You're like, oh, prove it. No, you can. I'll just set it right here. You can stare at yourself all you want. But that's the point. Each photon doesn't have very much energy. But if you got a whole bajillion photons, which is that's the power output of my laser. It's a bajillion photons per second. Then all those photons pile up. Okay, I think we are done. All right, one last question, then we're done. Alexa, cancel. Okay, of ultraviolet and infrared. So ultraviolet is literally above violet. It literally means above violet. So if you look at the diagram, which is on the board and up here, ultraviolet is that direction of violet. Roy G. Biv. Infrared literally means below red. So infrared is that way, below red. So answer the question. Of ultraviolet and infrared, which one has a larger wavelength? Take a minute and talk to your neighbor. Which one has a larger wavelength? Yeah. Good luck. Stay healthy.
At least
It'll be two. Okay. Remember, energy is tied to frequency. If frequency goes up, wavelength goes down. If frequency goes down, wavelength goes up. So, of ultraviolet infrared, which has a larger wavelength, if you believe the answer to higher wavelength is ultraviolet, raise your hand. If you believe it's infrared, raise your hand. It's infrared. Infrared has a longer wavelength and therefore a lower frequency and a lower energy. Now, which one has a higher frequency? Now you should definitely get this one. If you believe that ultraviolet has a higher frequency, raise your hand. Good, you should all have your hands up. Ultraviolet has a higher frequency because ultraviolet has more energy per photon. It literally means better than violet or stronger than violet. And then, which one moves faster through space? Same. They're the same. They're the same. Because they are both light, they both move through space at the same speed. Okay, if you haven't watched the video, please do so, the video guide, because it's really good. It's got a lot of good information in there.